So, are there any questions before we begin? Any questions from yesterday? If no questions, can someone remind us what we were talking about yesterday?
Trigonometry.
Yes, we introduced this field of trigonometry, and I gave you a very historical introduction into trigonometry. We talked about Aryabhata and Hipparchus and Eratosthenes and the Sumerians and the Babylonians. So it was a day full of history. So I hope that was a sufficient introduction. What were the key things that we learned about? If I have this triangle and some angle here, theta, we defined various relations between sides. And those things were called sine, cosine, and tangent. And so the sine of theta, okay, I'm going to ask someone. So say that this is A, B, and C. Okay, so let's see. Brianna, can you tell me what the sine of theta is here?
Do they have on the prices right yesterday?
Okay, give me a second here. I'm going to mute everyone. Okay, so now if you would like to speak, just unmute yourself. So let's see, Brianna, your name was the first one I saw. So can you tell me what the sine of theta is in this drawing? Okay, nothing. So so first, I'll just do it. So sine is defined to be the opposite over the hypotenuse, and so right here we have this thing SOHCAHTOA. This is what we talked about yesterday, and so the opposite leg is B, and the hypotenuse is C. So that's B over C. Can someone tell me what the cosine of theta is? Anyone?
A over B.
No, it's not A over B. That's actually cotangent.
A over C.
A over C, yes. Adjacent over the hypotenuse. And then what is tangent? Anyone?
A over B.
It's not A over B. That's actually cotangent. But we're going to talk about the co-functions.
B over C.
Okay, no, that's sine.
B over A.
B over A.
B over A, good. So there are only 6 possibilities, right? So it's okay. As you get more familiar with these things, this will become almost second nature. And again, don't memorize the letters, because the letters don't have anything to do with the triangle. Memorize the relations of the legs. Okay, so we yesterday, people did really well on this activity. You made your own table of values, and I emailed around 11:30, and I said, please memorize these values, especially the 11th and 12th graders. There is great value in memorizing these important, all the angles that I gave you were important for like 35, 30, 45, 60, 90. Those are all very important angular measures, and they come up in nature everywhere. So hopefully you have memorized these things, because we'll be referring to these things lots today. And so basically, in summary, we have found sine, cosine, and tangent. We have found the values of these things for angles between 0 and 90 degrees. And I would like to summarize those results that you found. And most people did everything correctly. So this is sort of part 1 of yesterday's activity. And I'm going to sort of quickly just do these and give you these values. In case you got anything wrong, we can sort of talk about why these things are the way they are. So we talked about how this is these 2 things are special right triangles, and how how there are certain relations between these legs. And for the 45, 45, 90 triangle, it's 1, 1, square root of 2. This is like the tent. The ancient people wanted to know how to build their tent, right? And this one is 1, 2, square root of 3. So for sine of 30, I will be referring to this rightmost triangle. And so look, 30 degrees, sine is opposite over hypotenuse, so this is 1/2. Okay, sine of 45, now I'm going to look at this graph here, and 45 Okay, so sine, so opposite over, so I'll refer to this angle because we have 245. So opposite of this angle is 1 divided by square root of 2. You could write that as 1 over the square root of 2, but that's the same thing as square root of 2 divided by 2. Either notation is fine, okay? If you're confused as to get from here to here, don't worry. All you do is multiply the numerator and denominator by square root of 2. We're going to talk about rationalizing the denominator later in the course, towards the end of the course. So anyway, so 1 over square root of 2 is a fine notation for now. Sine of 60. I'm going to look at this graph and opposite over hypotenuse. So here's my 60-degree angle. So opposite, that's root 3. Here's the hypotenuse, 2. So root 3 over 2. Now I'm going to do the same things with cosine, but look how I've written this. Cosine of 60. So I'm going to look at this graph. Well, cosine is adjacent over hypotenuse, so that's 1/2. Do you see how the sine of 30 and the cosine of 60 have the same value? They both have 1/2 as their value. Because they're referring to the same angle. See, sine of 30 is this divided by this, and cosine of 60 is, again, this very thing divided by this very thing. That's why they have the same value. So there's this apparent symmetry that's starting to happen. How about cosine of 45? Well, I'll use this angle again. Well, cosine of this angle is adjacent over hypotenuse, and again, I get 1 over square root of 2. So these things have the same value. And now cosine of 30, you might guess, based on this pattern, cosine of 30 is adjacent over hypotenuse, so adjacent over hypotenuse, and that's root 3 over 2, and again, these things have the same value. So there's a symmetry here between sine and cosine. So apparently, cosine takes on the same values that sine does, just for different degrees, right? And we're going to, this relationship will become very clear today by the end of the lecture. And then we also found the values of tangent for these various angles. And tangent does not have a symmetry, it does not have a symmetric trigonometric function, in the sense that it doesn't have like an analog that it doesn't, so sine has cosine as its symmetric pair. Tangent doesn't have that among these basic trigonometric relations. Yes, but we're about to find, as Nishan said, that sine divided by cosine is tangent. So first, I'd just like to find tangent of 30, tangent of 45, tangent of 60, and then we'll see that indeed sine divided by cosine is tangent. So tangent of 30, I'm going to look at this one here, and tangent is opposite over adjacent, so that's 1 divided by square root of 3. You could also write this as root 3 over 3 if you wanted to. Tangent of 45, well, I'm going to look at this graph, and okay, so that's opposite over adjacent, right, for tan, and so that's 1 divided by 1, which is 1. And then tangent of 60, again, on this right triangle, opposite over adjacent, that's square root of 3 divided by 1, which is square root of 3. Okay, so we have these various values for tangent. And now it turns out that, okay, look, tangent of 30. It turns out that if I take sine of 30, which is 1/2, and I divide that by the cosine of 30, I get tangent of 30. And indeed, you could verify sine of 30 divided by cosine of 30. Well, sine of 30 is 1/2. And if I divide that by cosine of 30, which is root 3 over 2, I could also, so this is a complex fraction, which is not preferred, but I could write this as this. And indeed, I got 1 over square root of 3 because these 2's cancel. And you could do the same thing for tangent of 45 and tangent of 60. And let's just do it. Tangent of 45, well, that's easy. Sine, it's sine of 45 divided by cosine of 45. Well, sine of 45 is equal to cosine of 45. So obviously that's 1. So that gives us what we expected. And tangent of 60, you can verify that that's sine of 60 divided by cosine 60. And indeed, sine of 60 is that divided by cosine of 60. Well, dividing by 1/2 is the same thing as multiplying by 2. These 2's cancel, and you're left with the square root of 3. So this is very important, that generally tangent of any angle x, or let's use theta. Tangent of theta is defined to be sine of theta divided by cosine theta. So if you know what sine of theta and cosine theta is, if you know what both of them are, then you immediately know tangent. So in math, we often talk about the least amount of information that we need to solve a problem. And this is a big sort of topic in linear algebra, in the field of linear algebra. And you'll find that sine and cosine are sort of all you need. In a sense, because tangent depends on both sine and cosine, it's not its own independent function. So it doesn't tell you anything more that you wouldn't have with just sine and cosine. However, it is a convenient way to describe the relationship between sine and cosine. Okay, so this is something worth writing down if you were not familiar with it before. So let's just plot these various functions, right? Sine, cosine, tangent, they're all functions. Let's plot their behavior from 0, here's the value of 0, and here's 90. So this axis here, I'll use red. This axis here is my angle, theta, and this axis here is my function, y. And so I'm going to first do this for the sine of theta. And okay, so let's do it this way. The sine of theta will be in red. The cosine of theta will be in blue. And the tangent of theta will be in black. Okay, so starting with sine, just with the values we have. What is sine of 0? Well, you found yesterday on the quiz, in the second part of the quiz, in that guided activity, that sine of 0 is 0. And you did that by stretching out one of these triangles, you might remember. So sine of 0 is 0. Okay, sine of 30 is 1/2. Well, that's like, say that this is 1, okay? So sine of 30 is halfway up. And sine of 45 is 1 divided by square root of 2, which is a bit more than 1/2. So it's, about here. Sine of 60 is still a bit more. And then sine of 90 you found was 1. So, okay, so this wasn't super well drawn, but if I were to connect the dots, you have this arc. Okay. Do people see it? It's not very well done. Okay, let me just draw a schematic arc. Okay. It kind of looks like that, if I had drawn the points better. Okay, so this is sine. So, okay, let's do cosine now. Cosine of 0. Well, you found yesterday on the quiz that cosine of 0 is 1. Again, by stretching one of these triangles and considering an extreme case. Cosine of 60 is root 3 over 2. Well, that's pretty close to 1. Root 3 over 2 is like 0.86 or something like that. So it's somewhere up here. Cosine of 45, well, that's equal to the sine of 45. So the graphs cross here. Cosine of 60 is 1/2. And cosine of 90 is 0, as you also found on the quiz. So this came out better. And so connecting the points gives me this line. And now the tangent. So yesterday on the quiz, you found that the tangent of 0 is 0. Again, by doing that stretchy business, right? I don't know why it's not letting me draw a point there. Okay, anyway, 0. Tangent of 30 is 1 over square root of 3. Well, that's a bit more than 1/2. So that's somewhere about here. Tangent of 45 is 1. So it's here immediately. And then tangent of 30, tangent of 60 down here, that's root 3. So that's greater than 1. And tangent of 90 is not defined. So this here is an asymptote. And so generally the behavior, again, I did not draw this as well as I could have, but the general behavior of tangent is that it increases without bound here. Okay, so do people see this general shape? And okay, that was not well drawn. Should have gone more like, should have increased faster. So it goes up like that. And it goes off to infinity in this direction. Okay, so we have these shapes. And you might be curious to know what happens before 0 and after 0. I think that's a very reasonable question because it looks like these are interesting shapes. They're curves. And and they're functions. And just as, if I were plotting a parabola, you would want to know what happens. If I just plotted this much of a parabola, you would also want to know what happens below 0, below the point x is 0. And we would find that, it's a symmetric function. So we should ask similar questions for these new functions that we're being introduced to. What happens after this point and before, after 90 and before 90? So first of all, does anyone have any questions about this? This is sort of a recap of what we did yesterday and what you did yesterday on the assignment. Nishan says no questions. Okay. Do not hesitate if you do have a question. So the goal of today is to go further. We're going to go below 90 and above 90. But first I would like to introduce to you, this is sort of an aside, okay, because it's not as relevant. But I would like to introduce to you an easier way of measuring angles, a more convenient way of measuring angles. So we're going to extend our notion of these graphs after we talk about this little aside. And for the purpose of the rest of this course, I think, I will be referring to angles in degrees. The way I'm about to show you to measure angles, however, is a more professional way to measure angles. And the juniors and seniors will find this particularly helpful. Because in the field of calculus, you cannot use degrees. You can only use this new measure that I'm about to tell you about. So this is sort of an aside. Okay, so we're going to return to this trigonometric graph activity in just a bit. So our current way of measuring angles is in degrees. And can someone remind me the origin of degrees, where it came from? Those of you who like history. Where did degrees come from? Why are there 360 degrees in a circle? Anyone?
Because there were the people who saw the sun going around and they thought it takes 360 days for it to go around. So it's
That's very good, yes. Degrees. That's exactly right. The Babylonians saw that the sun travels 1 degree in the sky every day. And over the course of a year, the sun traverses the entire celestial sphere. And thereby going what they thought is 360 degrees. And so they defined 1/360th of a circle, just one little sliver of this, to be 1 degree. This is much more than a degree, but they defined 1/360th to be 1 degree. And so that's where degrees comes from. And so it's a very anthropic. We call units of measure that are this sort of based on the human experience as anthropic. And anthropology is the study of humans, so you can see the origin of this word. Okay, so this is not, so I mentioned yesterday that if there were people on other planets, if there was other intelligent life in the universe, that life would definitely not have the same notion of degrees because they would live on a planet that doesn't go around the sun in the same amount of time. That's what degrees is based on, right? The amount of time it takes for the Earth to go around the sun. They would have their own measure. And so degrees, it's not a universal way of measuring an angular amount, and therefore it should be abandoned. It's an ancient. It's like the customary system with inches and feet and stuff. It's like not a very fundamental thing to nature. The foot is based on the human anatomy, and that's not somehow, that's not related to the stuff that makes up the universe. So let's choose a measuring system that is more universal. And this measuring system would be based on the circle itself. And as we talk about, extraterrestrial intelligence, you should know that there was a famous, there were 2 very famous space probes in the 70s and 80s that are still going. Actually, they're the only objects that have left the solar system, and they're called the Voyager Spacecraft. There's Voyager 1 and Voyager 2, and they're beyond the orbit of the Kuiper Belt, which is like where Pluto resides. So they're outside the solar system, and soon they will be leaving what is called the heliopause, which is the sort of solar wind of the sun, and they will be truly in interstellar space. But on the Voyager aircraft, there were messages to aliens. If aliens found the Voyager, and there was this thing called the Golden Record, on which Carl Sagan was the guy who was really in charge of this. He wrote the position, the coordinates of the Earth, and he referred to things in radians in this new universal angular measuring system, because he knew that intelligent life could share this notion of angular measure. And that's the notion that we're about to describe. So every circle has a radius, right? Okay, so Larissa said they put everything they wanted aliens to see. Yes, they put pictures of humans. They put sounds from planet Earth. It's really amazing, I think, what they did. Okay, so every circle has a radius. So here's a circle, here's its radius. Now, if I wrap this radius, so imagine it's a piece of string. Okay, now I'm going to wrap that. So it's flexible, right? So I can bend it. I'm going to put that radius along the arc of the circle. And it's going to look something like this, right? Didn't look too good.
Yes.
Yes, thanks. Okay, so the length here is r. And we define as well, right? So this is r and this is r. It's the same piece of wire. And the angular distance now that this rope subtends, the amount of angle that it covers on this circle, in other words, this angle, it corrected that into a triangle. But anyway, this angle here is defined to be 1 radian. So 1 radian, this takes a bit of thinking. 1 radian is the amount of arc subtended. Subtended means covered, in an angular sense. The amount of arc subtended by a radius wrapped around the arc of a circle. So what is the circumference of a circle in terms of r? Can anyone tell me? The circumference is not pi. The circumference is a function of r. Can anyone tell me? Okay, you all should know this. What is the circumference of a circle?
Pi r.
It's not pi r, it's pi d, which is 2 pi r. So you're close, but. Okay, so Audie, you said no, 1 radian is pi. No, 1 radian is not pi. I hope that makes sense to you. 1 radian is not pi. 1 radian is like 40 something degrees. Okay, anyway, Audie, we can talk about, I think you might be confusing something. So we can talk about that later. Yes, so, okay, so many people now are messaging me. No, okay, so some people said that the circumference is pi r squared. No, pi r squared is the area, okay? The circumference is 2 pi r. Okay, and so if the circumference is 2 pi r, then can someone tell me how many radians there are in a full circle?
Infinite.
Say that again?
Infinite.
8.
No, so
360.
it's not infinite. So someone said infinite.
8.
So
2 pi.
okay, so yes, so 2 pi is correct. So my question, let me reiterate my question. If I started here, okay, and I walked all the way around the circle, right? What is the angle I would have subtended? So first of all, what is the distance I would have subtended? That's given by the circumference. Say my radius is 1 for convenience. Then I will have traveled 2 pi around as a arc. But the radian is the arc, right? The radian is, I've taken this distance here, r, and I've thrown it around the circle. And that exact amount is how we define the radian. So if the radius is 1, then 1 radian is just that radius wrapped around the circle. And so if I have 2 pi, if my, so basically I've identified, I've equated an angular measure with a measure of distance. That's the power of the radian. So the circumference of a circle is 2 pi, and if the radius is 1, that means that the total number of radians in a full circle is 2 pi radians. And so half a circle is pi radians because half a circumference of a circle of radius 1 is pi. So in other words, going around this way, going halfway around, this angle is pi radians, right? This angle, 90 degrees, is pi over 2. So on and so forth. Okay, so does this make sense? I fear that I did not explain this super well. But basically, 1 radian is the angle subtended by the radius when wrapped around the arc of a circle. And so when you wrap the circumference around the circle, when you then you've gone all the way around the circle, and therefore there are 2 pi radians in a full circle. Okay, so I hope that makes sense. But the main thing you really need to know is this conversion factor of how to get from radians to degrees, because many of you will be thinking in degrees, and in fact, for the rest of the course, like I mentioned, we will be working in degrees. But for those of you who are going to be taking pre-calculus or calculus soon, you will need to get used to radians. And this is the conversion factor, and it's based on the fact that I just said, that if you go halfway around a circle, that's what we used to think of as 180 degrees, right? This amount, a straight line, right? This angle, that's 180 degrees. And we also just said that that's half the circumference, which corresponds to pi radians. Okay, so sorry, I lost track of the chat. Solina said, how many radians are in a circle? 2 pi radians. And Nishan said 180 over pi for degree. Yes. And that's the conversion factor I just said. So if you're trying to convert from degrees, remember our discussion of dimensional analysis and how when you're trying to convert from like feet to inches, say I have 6 feet and I want to get this in inches, well, I'm going to multiply this by a fancy form of the number 1, and that form is given by 12 inches by 1 foot, right? This is really the number 1 because it's the same unit of measure in the numerator and denominator. Sorry, it's not the same unit of measure. It's the same amount of measure, right? 12 inches is equal to a foot. And therefore, physically, this quantity is 1, right? Even though the number itself is not. The number is 12, but dimensionally, this thing gives you 1. So I've preserved, multiplying anything by 1 preserves that thing. And so by multiplying 6 by 1, I haven't changed 6. I haven't changed the physics of 6. But the units do change, and the feet cancels, and I got 72 inches. Same thing here. This is a conversion factor. This is analogous to your 12 inches by 1 foot. So this is what you would use. This is what you would multiply some value in degrees. So say I had 90 degrees, right? And I wanted that in radians. Well, I'd multiply this thing by this fancy form of 1. And usually, because radians are a dimensionless unit, we don't even write radians. You don't have to write, we have the sign for degrees, but you actually don't need a sign for radians at all because it's dimensionless. And 90 divided by 180 is 1 over 2. And so here you get pi over 2. So let's just do a few of these so you get some practice. And there are more of these types of problems on the homework. So converting 30 degrees to radians. Well, what would I do? I would multiply this thing by pi over 180 degrees. And 30 divided by 180 is what? 1 over 6. And so 30 degrees is pi over 6 radians. And this will become second nature to you. When you see pi over 6, you'll think 30 degrees. How about 270 degrees? I'm going to do the same thing. Multiply this by pi over 180 degrees. And 180 divided by 270. Can someone tell me what 270 divided by 180 is? Do it in your head. What are both divisible by? Yes, it's 3 halves. And so this is 3 pi over 2. So you'll get lots more practice converting from degrees to radians on your homework. Okay, so anyway, so now let's return to sort of so this was an aside that I had placed in there just to introduce people to radians. But for the remainder of this course, we're going to use degrees. Okay, so let's return to our idea of extending our notion of these trigonometric values beyond 0 and 90 degrees. And here I've drawn the land that we've covered, so to speak. We've covered, 30 degrees. We've covered 45 degrees. We've covered 60 degrees. We've covered 90 degrees, right? So all of these triangles, all these right triangles, this angle here, this is different for each of them. But we know now sort of what the basic shape is of the function sine, cosine, and tangent. So now our task is to extend, to break beyond this quadrant. And you can see that if I connect the tips of these triangles here, they create a circle. They create 1/4 of a circle. And we're eventually going to find what happens when I extend this circle all the way around, right? And you're going to get analogous triangles. And this is what we're about to do. We're about to find the trigonometric values of these angles, right? Angles that are beyond 90 degrees and below 0 degrees. So let's start with this quadrant. So does what we're trying to do make sense, first of all? There is a distinction between doing something and then understanding why we're doing it. We're trying to break. Who said that?
Rosie.
Rosie, you do get it or you don't get it?
Yes, I get it.
You get it. Okay, great. So for those who don't get it, we're trying to find the values of trigonometric functions beyond 90 degrees. So when you had this really thin triangle here, like this one here, this was like really close to 90 degrees. And this is what I asked you to do on the quiz yesterday. I basically said, extend, I had another way of thinking about it, but I basically said, make this point, get as close to this tip as you can, and then consider what like the sine of 90 degrees, cosine of 90 degrees, tangent of 90 degrees is. And you found that tangent is undefined, so on and so forth. Okay, so let's start by venturing in this direction. So 90 degrees is, this is where we start measuring. Okay, 0 degrees is always to the right, and then you measure degrees counterclockwise. This is the convention. So this is 60 degrees. This is 90 degrees. So 120 degrees would be right here, right? Just 30 past 90 degrees. This is 120 degrees. And 180 degrees would be in the opposite direction. So this is the direction we're headed in this general counterclockwise direction. So 120, our first stop, so to speak, if we're riding a bus, okay, or even better, I think, it's like planetary motion, we're going in circles. So 120 degrees is our first stop on this planetary journey. So 120 degrees. Well, that means if I draw this triangle, right? So this angle here, this is 120 degrees. But this angle is 90 degrees. So how much is this angle? Look, it's just subtraction. This is 120, this is 90. So this is 30, right? Okay, I hope that makes sense. And that means that this is 60 because this is 90 degrees. This entire thing here is 90 degrees. So this is just basic geometry. We haven't talked about really the fact that, anyway, okay, I hope this is straightforward enough for people. So 120 degrees. You can basically think about this as a triangle just in the opposite direction, right? Subtending 60 degrees. And then we have the same trigonometric relationships, right? So except now this is in the negative direction, right? This leg here is in the negative direction, and this is in the positive direction. So sine of 120, right, is going to be the same thing as, can anyone tell me?
Cosine of negative 120?
That's not correct, but that's a good guess.
Cosine is 60.
Okay, so sine of 120 degrees. Okay, who agrees?
30?
It's the same thing as cosine of 30. Okay, so basically what I've said is that instead of thinking of the sine of 120 degrees, I'm going to think of this as the sine of 60 degrees. See how this entire angle, okay, wait, I don't think you can see that. Okay, I'm gonna redraw this graph here. Give me a sec. Okay, so we want to find, okay, so Aditya is correct. We want to find the sine of this angle, right? But we know that this angle is 90 degrees, right? Just from here to here. And so this little bit that's remaining, is 120, because that's what the big angle is, minus 90. 120 minus 90 is 30 degrees. And lastly, we know that this angle, this entire angle, that's 90 degrees. And so this little bit is 90 minus 30, which is 60. And so if we find the sine of 60 degrees, right, for this triangle, that's, you know, if you considering that this leg here is in the negative direction, then sine of 60 will be the same thing as sine of 120. So this is what I'm saying. The sine of 120 degrees is the same thing as the sine of 60 degrees, just through this little bit of geometry that we've done. Okay, so this is sort of, yes, and Nishan gave me the right answer. It's root 3 over 2. But okay, I know that this is sort of a lot to get your mind around because we're going in a negative direction and we have negative angles. Okay, can someone tell me what the cosine of 120 is? Now this is where it gets a little trickier because it's not just the cosine of 60. Remember, cosine is adjacent over hypotenuse, but now our adjacent leg is in the negative direction. See, this was our positive x direction. And now our adjacent leg is negative. So this is equal to negative cosine of 60. Okay, and negative cosine of 60 is negative 1/2. And lastly, tangent of 120, that is opposite over adjacent. And again, our adjacent leg is in the negative direction. So that's going to pick up this negative sign. So it's going to be negative tangent of 60. And we know that to be, can someone tell me what tangent 60 is?
It's just 1.
Tangent 60 is not 1.
Oh, sorry. It's just 3. So it'll be negative 3.
No, it's a square root of 3. And so the negative sign will give you negative square root of 3. Okay, so I would write this down. We're going to get more practice of doing this. Lots more practice. Okay, so if this little bit was confusing, let's now do 135 degrees. Okay, so if I'm 135 degrees around the circle, and this is 90 degrees, then can someone tell me what this angle is?
45.
45, and what is then this angle, the relevant angle? It would also better be 45, because 45 plus 45 is 90, and that total angle is 90 degrees. Okay, so now we can play the same game and ask ourselves, what is the sine of 45, cosine of 45, but using this as a negative leg, right? That's the only difference. This side has a negative distance because this was the positive direction. Now we're in the opposite of the positive direction, which corresponds to the negative. So sine of 45, sine of 135 is going to be equal to the sine of 45, and it's because both of our legs are positive, opposite over hypotenuse. And what is the sine of 45? It's
root 2 over 2.
Good. How about cosine of 135? Now this is the tricky one because we have a negative leg. So this is equal to negative cosine 45, which is negative square root of 2. See, this adjacent leg over the hypotenuse, and this adjacent leg is in the negative direction. So that's what causes this negative sign. And now tangent of 135, again, we're going to have a negative sign because this negative leg is involved in opposite over adjacent. And this is negative tangent 45. And what is tangent of 45? Well, that's 1. And so negative tangent 45 is negative 1. Okay, so is this making sense? Let's do a few more. What if I had 150? What if this angle was 150 degrees? Then what is this angle?
30.
30, good, because the total is 180. And so if this is 30 degrees, then what is the sine of 150?
No, half.
Well, no, it's just equal to the sine of 30, right? Because I have the same legs involved, right? I have a positive leg here. That's basically the same exact case as this, right? I'm taking the ratio of this leg to this leg, and we know the sine of 30 to be 1/2. The cosine of 150, now I'm going to have a negative sign because of this negative leg. And so this should be equal to negative cosine of 30. And we know that cosine of 30 is root 3 over 2. And so negative cosine of 30 is going to be negative root 3 over 2. So I'm going kind of fast because I want this. This is something you can work out on your own. I was planning on doing all of these, but I'm now realizing that that's not going to be possible in the time we have. But that's okay, because once you sort of see how I'm doing it, you can work the rest out. Tangent of 150. Well, that's equal to the negative tangent. Again, I have the negative sign because it's opposite over adjacent, and this adjacent leg is negative. Negative tangent of 30, and tangent of 30 is root 3 over 3. So now you can see why it's important to have these values memorized. Sine 60, cosine 60, so on and so forth. Okay, so you can continue, and I was hoping to do this today. But let's just do at least a few more. We'll do a few of these, and then we'll make a total, a sort of conclusive sketch of sine, cosine, and tangent. So now so say I want to know what the sine of 210 degrees is. So 210 degrees is this big angle here, huge angle, more than 180 degrees. So if this entire green angle is 210, can someone tell me what this angle is?
30.
Very good, 30, because it's 210 minus 180. And so this angle here is 30. And so the sine of 30, the sine of 210 is going to be, now look, I have now two negative legs, because see, this was the positive direction. Now both of my legs are in the negative direction. And so, yes, so people who messaged in the chat were correct that the sine of 210 is equal to negative sine of 30 degrees. And negative sine of 30 degrees is negative 1/2. Similarly, cosine, again, I have negative leg and negative leg. So this should be negative cosine 30. See, because cosine 30 is, cosine is adjacent over hypotenuse, and my adjacent leg is negative. So this will be negative root 3 over 2. And then tangent of 210. Well, here, now I have the ratio of two negative legs. Negative divided by negative is positive. So this is just going to be positive tangent of 30. And we know that to be root 3 over 3. So you can keep going, keep playing this game. But this is basically what Aryabhatta was doing in ancient India when he made his famous list. He was only doing this for sine. We're doing it for tangent and cosine as well, which is pretty impressive. But anyway, you can have fun with this and construct your own table. But I'd like to skip to the sort of punchline. And that is that if we were to plot all of these things simultaneously, so if I truly did all of these values, if I computed all of these things and then I were to plot all of them, plot all these points, let's start with sine. Say I were to plot sine of theta as a function of theta. I would get a graph. I'll zoom in because these numbers are small. I would get a graph that starts here, right? Sine of 0 is 0, and then it increases, and then it hits, this is the point 1. And then it starts decreasing, right? We found that sine of 120 is root 3 over 2, right? And then we found that sine 135 is root 2 over 2. Here, sine 150 is root 3 over 3. And then back, back here at 180, it hit 0 again. And then if we continued our journey, when we hit 210, we started finding, I'll zoom back out so you can see sort of the progression. We found that sine of 210 gave us a negative value. See, sine of 210 was negative 1/2. Here it is, negative 1/2, right? So now the function starts going in the negative direction. So negative 1/2, and then it makes the same pattern, increasing until it hits 1. There should be more curvature here. And then it decreases again until it hits 0. So our basic shape, you can start seeing, it's like a wave. In fact, it is a wave. So this was our, if we had truly found all the points and plotted all the points, which would have taken more than the time we have, this is what we would have gotten. And so we did this exactly for these first, this is how I started the lecture. I plotted these points, and then I did a few. I did 120 and 135, and then I also did 210, just to show you the general shape. So this is what you get when you plot the sine of theta, and it continues actually. If you were to keep going, so 360. What comes after 360? Well, if I were to do the same analogous, it would be 390, right? And then increasing by 15 degrees, 405 degrees, and basically the pattern continues, right, in either direction. So it's a repeating waveform. Okay, so does this make sense? That when I plot the values, I got this shape, and that it repeats. It doesn't make sense. Well, I mean, when you repeat, what you've really done is you've started going around the circle all over again. So I have sine values 0 to 90, sine values 90 to 180, sine values 180 to 270, and then sine values 270 to 360. And now that here's the point, 360 degrees. Now that I'm at 360 degrees, now everything repeats itself, just as if I were at 0 degrees again. And look, when I'm at 0 degrees, I have this behavior. And so this chunk of the graph basically repeats itself on and on forever. Okay, so I hope that makes sense. Let's do the same thing for cosine. We found just in the beginning of the lecture today that cosine of 0 is 1, cosine of 30 is root 3 over 2, cosine of 45 is root 2 over 2, cosine of 60 is 1/2. This is not really to scale. More like that. Cosine of 90 is 0. And then we also found, look, I'll go back up for 120 so you can at least trust me. For 120, we found that, see, cosine is negative. So now we see that the cosine goes into the negative axis, goes into the negative y-axis here. So look, 120, now it's negative 1/2, on and on, right? And now it's negative 1. And now it's going to repeat itself. See, for 210, it started decreasing, and then it hit 0 again for 270, and then it increases back to 1. And so when you're back at 360, it should be, again, more curved. When you're back at 360, you're at the same point as you were at 0 degrees. And that makes sense in light of the fact that we're going around a circle, and you've arrived at the same angle, right? The same angular position. So this is the shape of cosine. It's also a wave. And now comparing sine and cosine, okay, I'll extend the wave a little bit so you can sort of see the general shape. So what do you notice about the shapes? This is not a good graph. What is similar about these two graphs? Well, they have the same shape, right? Look, they both rise and fall at the same rate. They both, they both go up and down at the same axis. But what is different is where they start. See, sine starts at 0. See, sine started at 0. Cosine started at 1. And you can see that actually if I were to superimpose these images, so I'll graph sine here, that they're offset, that sine is offset by 90 degrees. In other words, if I shifted this cosine graph over to the right by 90 degrees. Did someone say wait? Okay. If I shifted cosine over by 90 degrees, I would get sine, right? So this green graph is shifting something to the right 90 degrees. And we talked all last week about how if you want to shift something to the right by 90 degrees, you have to subtract from the argument by 90. So this is a famous thing in math, that the sine of theta is equal to cosine theta minus 90 degrees. So you can write the cosine in terms of sine this way. And this is the result. Remember at the very beginning of the lecture, we had found that there was this sort of, when I had written that table of values, see here, this table of values, how I said that sine of 30 is cosine of 60, sine of 45 is cosine 45. See, I said that there was this apparent symmetry here. Well, now I have derived sort of, for you graphically, I've derived that symmetry in all its grandeur, that the sine is just cosine of the same angle minus 90 degrees. And lastly, right before, let's see. Lastly, we have tangent to fill out. And tangent, we said in the beginning of the lecture, well, its behavior down here, it starts at 0 and then it increases unboundedly until you hit 90, right? And then if you look at our table of values that we just created for angles greater than 90, tangent is also undefined for okay, so basically tangent changes sign. So it's, I guess I didn't show this exactly, so you have to take my word for it. But basically tangent, let's see here. Yeah, so tangent will, I want to make sure I'm drawing this right for you. 90 to, yeah, so, okay, so going, usually it's drawn in the negative direction here as well. And so we have something similar, and it's a repeating pattern. And so as you approach 270, my spacing is not perfect here, but as you approach 270, you'll have another asymptote, right? And it keeps repeating this pattern. And it crosses the x-axis at like 180, at 0, 180, 360, so on and so forth. So this is the pattern for tangent. I would like to show you that I'm going to graph something on a better, I'll graph something on my computer. So it's more, what is an asymptote? Okay, so someone asked me privately, what is an asymptote? An asymptote is a value that, I should have said this. An asymptote is a line or a general shape that the function in extreme values does not touch. So that the function will approach this value on and on, to eternity, but it will never touch this line. And same with this line and this line. That's what an asymptote is. So if you haven't taken Algebra 2 yet, I don't expect you to be familiar with that. But anyway, can you all see my screen here? Can you see this? Someone tell me.
Yes.
Great. Okay, so here's my sine function. So the computer knows that this is sine. So this is basically what I just graphed. And here's cosine. And we talked about how they're offset. It's funny, they use the same exact colors that I used, red and blue. Sine is offset from cosine by 90 degrees. And so indeed, that is strange. Oh, it's because it's in radians. Sorry. Okay, so you can see that here's the cosine graph, and if I move it over by 90 degrees, which is the same thing as pi over 2, now the sine and cosine graphs are overlapping. So if I moved it over by a very small amount, you can see how they're overlapping now. So anyway, so this is a verification of that result. Now I would like to divide sine by cosine. So I'm gonna do this, sine divided by cosine, because supposedly this is tangent. And indeed, we got the same exact shape that I just drew for tangent. See it was even in blue. See how this was my graph for tangent? Well, here indeed, you got the same shape. So anyway, sine divided by cosine is indeed tangent. Okay, so we've sort of we've discovered the shape of sine waves and cosine waves, as well as tangents. And these shapes will prove to be immensely important in what we do in the next few days. So I'm going to send out the quiz. The quiz actually does not have much to do with graphing, and it does not have much to do with trigonometric values beyond 90 degrees, because I thought that would be too new for people for it to be fair to quiz over. So really let's see here. Okay, not just Leanne. You all can see, I know you all can see my screen. Okay, so there's the quiz. Okay, so I think today might have been a lot for some kids. This might have been like more kind of too much information at once, because I know that especially ninth graders, this is like you just discovered what sine, cosine, tangent is. This is sort of a lot to take in. But does anyone have questions? I'll let you take this quiz and I'll stick around for a few more minutes. Feel free to ask questions.